something. I thought that recording was going the whole time. I'm going to pause this and look. I think it's still going. It just announced that it was working. So some books like to use capital F of X to show the original function. So rather than saying like G prime of X, they use F prime of X. And that's a big F. So you have your big F function and you take the derivative and you get the little f. That's a common notation in a lot of books. So for example, like let's say we know that the derivative is 3x squared. We could deduce, we know when we take the derivative of something with like a polynomial term, that we have to, like the power goes down by 1. This comes down and this becomes n minus 1. So doing like d dx of that, so like working backwards, we know that like if I have n minus 1, this, what I start with should be 1 higher. So let's say it's like x cubed. Is the derivative of x cubed 3x squared? Yes, it is. Now we'll take a look at it later on, like if f of x was something like 5x squared, how does that change? We'll take a look at something like that later on. How does that affect it? A way that you can go about doing it until you get an intuition for it. But we're not there yet. Okay. But that was just x cubed. What if I had like x cubed plus 7, x cubed minus pi, x cubed plus the square root of e? Like I could come up with a lot of bullshit. These are all constant values, though. That value is constant, that value is constant, that value is constant. So when we take the derivative of a constant, it goes away. And so those are all possible antiderivatives because their derivative is 3x squared. So these are all possible antiderivatives. So what we call, some books like to call it the family of antiderivatives. But what we get is like a general form. We're going to say the antiderivative of f of x on some interval I, we don't know what it is, but we have a region, is f of x plus a c. And c is a constant, okay? And that constant is called the constant of integration. It has a name. I don't know if I wrote it in the notes for later, so I'm going to write it down now. Okay. So let's look at finding all possible antiderivatives of 4x cubed. So the antiderivative, like we were saying, it must be 1 degree higher. And like I had said we could do earlier with like 5x cubed to figure it out, the way we would do it, or no, not x cubed, x squared, we would do ax cubed, as we're going to do in this process here, and figure out what a has to be. We're going to take a look at that process right now. So we know it should be 1 degree higher. We don't know what the coefficient is. Don't know this yet. Oh, and I wrote that. We don't know what a is yet. Ha. All right, so I'm going to do ax to the 4th plus c. And what we can do at this point is take the derivative. And if I take the derivative of this right here, I get 4ax cubed. And now at this point, I want to match up my coefficients. I got to match up my 4 with my 4a. Because 4ax cubed should give me the derivative of f prime of x should be f of x, and we had that up there as 4x cubed. So these should match. So I've got 4a equals 4. We solve for a, we get a equals 1. And we go back and we put that in right here and rewrite what f of x is here. Okay? So f of x is x to the 4th plus c. Why don't you guys try with 4 different ones? We've got f of x equals 2x, f of x equals 1 over x, f of x equals cosine x, and f of x equals e to the x. Pause the video, see what you come up with. You're trying to work backwards, figure out what the initial function is. Don't forget to include the constant of integration. Okay? I'll assume you did it. Let's take a look at what's going on. So if we have, this is like 2x to the first power. So to end up with an x to the first power, it had to start as an x squared. We don't know what the coefficient is, so we're going to put an a there. But this power went up by 1. Okay? You'll notice that's been a regular trend. I did this here. The power went up by 1. Okay, and so at this point, we're going to say f of x equals ax squared plus c. Then we'll take the derivative of it, and we get 2ax equals 2x, because the derivative at big F should be little f. And so we're going to match that 2x with this 2ax, and we'll see a equals 1. That doesn't always equal 1. Just in these initial couple problems, I had a equals 1. We will elevate our game shortly. So we have x squared plus c is our answer. So all of these, this generates, and I'm going to show you an example like graphically. The book calls all these different possible functions a family of antiderivatives, the online book, our OpenStax book. I have never seen the term family of antiderivatives before. Everybody else calls it a family of curves. So family of antiderivatives is the same thing as family of curves. Here's a graphical from our book that kind of shows it. I could have like, this is having a base of x squared, and then I'm just adding in a different constant. So my x squared, my basis graph is just x squared right here. You know what? Let's make this a smaller one like that. So it's a little tiny one like this. But if I do x squared minus 1, I've got a curve that it's this exact same curve, it's just down 1. And I could go up 1 instead. I could have, like x squared plus 1 and go up 1. And so there's a whole bunch of curves that look identical, just their height has changed. Effectively, they have a different y-intercept. That's the real shift. It does cause a change in the x-intercepts as well, but the graph isn't moving by the intercepts, it's moving up and down, so I'm going to focus on it just having a different y-intercept. Notice they call it family of antiderivatives. A lot of people call it family of curves, okay? And I'm going to call it family of curves. All right. We had a couple more to do. We had 1 over x. So if I rewrite 1 over x as x to the negative 1, it should mean like I started off with something that was 1 higher. Remember we did that? We went 1 higher. And so 1 higher than negative 1 would have been x to the 0. Okay? And I have that written down here. So I would have had ax to the 0 plus c. But note if I take the derivative of that, I get 0. 0 is not 1 over x. Not the same. And the reason why x to the 0 is 1. So like I've really just made this a constant. So apparently ax to the 0 is not the antiderivative of 1 over x. So now you got to stop and think about what did give a derivative of 1 over x. This is like a special case of a polynomial. If you see 1 over x or x to the negative 1, this was actually natural log. The derivative of natural log was 1 over x. I'm going to put a out in front because I don't know what the coefficient is. When we take the derivative, we do see that the derivative, or the a, ends up being 1 by equating coefficients. There's a 1 in front of this, and they have to match. But there's a little more to it. Like, X in general could be negative, and I can't have X is between infinity and negative infinity in general, but not here. So what I'm going to do is I'm going to put a little stipulation on the natural log of X. What we're going to do is we're going to say, instead of natural log of X, we're going to say natural log of the absolute value of X. And now if we stick in negative X, we still get a positive value. And everything works out just fine. Okay. Remember, absolute value of X, the function does equal X if X is greater than or equal to 0, negative X if X is less than 0. And if I did that here, I had natural log of negative X, and I took the derivative, it'd be 1 over negative X times the derivative of the inside is negative 1, which would end up still being positive X, 1 over X. So we do see that works. Okay? So that'll be natural log X. The other ones you did, we had cosine X and e to the X. Sine X has a derivative of cosine X, so the original function must have been sine X. If you went back and did it, e to the X is its own derivative. So the antiderivative should be e to the X as well. Don't forget your constant of, ooh, wrong pin. Don't forget your constant of integration on both of these. Okay. And that's it for this one. We'll do a more formal notation in the next video. Now, peace, crawlers. Peace.